Good day, good evening, and good morning. Welcome to another edition. In this session, we'll be looking at calculus, an introduction to first year university mathematics. The topic of interest for this session will be functions, of which it is splitted into the following subtopics: an introduction to functions, piecewise defined functions, composite functions, and even and odd functions. So let us get up to speed with the first topic, which is an introduction to functions. As a point of departure, let's consider f of x to be a function. If f of x is our function, there's a couple of things which I need you to understand. So how I want you to think of f of x is, think of it as an operation. So I need you to think of functions as an operation of some kind. So let's have a look at what is going on. So if we have a function, let's call it f of x, which we have above. What we know is that to a function, there's always an input, and our input here is going to be x. And x, which is our input, has what we call a domain. We'll quickly have a look at what that means. And once we put in our input to our function, we get our output, which is going to be y. And our y, as our output, has what we call the range. So if you remember from back in the days in high school, at some point you had to define what a domain is and what a range is. So if you remember, the domain is the possible x values which can be found for this function. So another way of defining the domain is as I wrote on the note here, which is the set of x values for which f of x is defined. And if you remember, the range was associated with the y values. So for the range, we are going to have its definition as the set of y values for which f of x is defined. With this outlined, let's quickly have a look at a diagram which will be helpful in you determining whether a function or whether a given expression is a function or not. So what you need to understand is there's the idea of one to many and many to one. So let's quickly have a look at the domain. So remember, the domain is the set of x values for which the function is defined. And then let's have a look at the range. So what I'm going to do is I'm quickly going to draw two circles. And inside these two circles, I'm going to put in x values and then put corresponding y values. So I'm going to have an x value, which is a. I'm going to have another one, which is b. I'm going to have another one, which is c, and then we have d. So on the other side, we're going to have the corresponding y values. So if you think carefully, we need f of a, because that would be the y wherever x is a. Then we need f of b, we need f of c, and then we also need f of d. What I want you to come to an appreciation is that for an expression to be considered as a function, the x value can give, or different x value can give the same y value, but different y values shouldn't come from the same x value. So what I mean is that you will have an x value which is going to give you f of a, like that. And then you will also have an x value which can give you f of b, like that, as an output. And then you also have an x value that can be c. Let's erase that. It can be c, but you'll find out that c also gives you f of b. That is allowed. And you can also have an x value which is d, which is going to give you f of d. So if you quickly zoom in and look at the gold part, you have two different x values that are going to give you the y value. That is allowed. But you can't have two different y values that come from the same x value. So you need to make a note of that. So if you look carefully here, I'll just say important. What you need to take away is that two different x values for a function can give you the same y value. That will still be a valid function. But if the function has two different y values which are mapping to the same x value, that does not qualify to be a function. Okay, so to demonstrate what I'm saying around the idea of two different x values giving you the same y value, and that would still be considered as a function, I will use an easy function which you already know, which is a parabola. So let's make some space here and quickly note down that if for the same, or if for different y values you have the same x value, then that is not a function. Okay, so let's have a look at an example to quickly understand what this mapping means here. So if you consider a simple example, which I will call example number 1, which is what you probably have done for a very long time. So what we are going to do is we are going to consider f of x equals, I'll just take an easy function, x squared. So if you look carefully, when we are asking ourselves, is x squared a function or not, the answer is easy. So if is f of x a function or not? So what we can do is we can quickly just plot f of x. So let's go and do so. So let's plot f of x. And by now what you should be aware of is if you want to plot any function, you have a couple of steps which you can follow. The easiest one is to quickly find the x-intercepts. And when looking for the x-intercept, what we know is that y is equal to 0. So our equation is y equals x squared. So if you make y to be equal to 0, you'll see that you'll have x squared equals 0, which means that your x should be 0. So if we quickly write this as a coordinate of the x-intercept, you'll see that we'll have 0 and 0. Then step number 2, whenever trying to plot a function, the easiest second thing to do is to quickly find the y-intercept. And for the y-intercept, what we know is that x is 0. So our function y is given as x squared, which means we have y equals 0 squared, which gives us 0. So if we write this as a coordinate, you should easily see that this will be 0. Then step number 3, for this graph, you should easily be able to see that because we have f of x equals x squared, it should be concave up. So step 3, I would call it concavity. Hopefully I didn't make a mistake. If I did, please correct it. If you look carefully, the coefficient of x squared, which is 1 or positive 1, means that we are going to have a concave up graph. This is just borrowing from knowledge which you probably learned back in the days. Now let's quickly draw our graph here. The turning point, you should know by now that it's going to be at 0. So step number 4, what you are interested in is the turning point. And for a quadratic equation, you should remember that the x-coordinate of the turning point is always given by negative b divided by 2a, like this. And if you look at our equation, it is what? 1x squared plus 0b plus c. So if you think carefully, when you substitute, you'll have negative 0 divided by 2 times 1, which will give us 0. So the x-coordinate of the turning point will be 0. So that the turning point is that. So it's easy now to find the y-coordinate of the turning point, because all what you do is you go and substitute your x-coordinate of the turning point, which in this case will be 0 squared, which is 0, so which means our turning point is at 0 and 0. Finally, we can now sketch this graph here for our step number 5. Let's quickly draw our Cartesian plane. And let's quickly draw our graph. So we already know the x and the y intercepts will be there, the origin at 0 and 0. So we have 0 and 0, and that's where also our turning point is at. And we said this is concave up, so that means I'm looking at a graph which is something like this. This is what my f is. My f is, or my f of x, that is the graph there which we are getting. Okay, but what I want to pass to you, and this is the reason why I drew this graph. If you can look carefully, if we have a x is 2 here, what you will know is that you will have a corresponding y value of 4 up there, because you'll just have 2 squared. But if you look carefully, you can also have an x is minus 2 the other side, but the corresponding y value of the function will still be 4, and this will still be a valid function. So that is why I said here, if you look at B and C, you can have different x values which will map to y values which are the same or equal. That is what we were saying this can still be a function. So essentially what you should be introduced to, which we'll probably do later, is the vertical line test. But outside that, let's quickly determine the range of this graph here. So remember, the range I told you, it's the possible, or the set of y values which the graph is defined for. So if we look at our graph here, remember y is going up and down. You will see that our graph starts having momentum from the y is 0 line, because remember that this line here is where y is equal to 0, the x-axis. So if you look carefully, our graph is defined from the x-axis going up. It doesn't exist below the x-axis. So that means that our range, we can write it in 2 ways. We can say y is an element from 0. And if you look carefully, our graph is not bounded as it goes up. We can say it can go up to positive infinity. And what is very important is that whenever you are writing infinity, infinity should always be next to a KV bracket. So infinity likes KV brackets. Essentially, we can't include infinity because we do not know the definite value of it. It's not definite. So make sure that you do not make that mistake. So never put a square bracket next to an infinity. Okay, make sure you take that note. So our range can also be written as y is greater or equal to 0. Okay, so starting from 0 going up, that is our range. So remember, our range we defined previously as the set of, my mistake here, because we're looking at the range, it is supposed to be the set of y values for which f of x is defined. Okay, my apologies on that. Now let's have a look at our domain. So remember, for our domain, we said it is the possible, or it is the set of x values for which the function is defined. So for our domain, if you can look carefully, remember domain has to do with x. Nothing is stopping our graph from having x values which are going to the left and going to the right also. We have no asymptote here. So what we would typically do is we would say x is an element of, in such cases, of real numbers. Someone else would prefer to say x is an element of, since the x can go even to negative infinity, they would put in negative infinity like that, and then put in positive infinity like that. That is still a valid answer. So make sure that you get familiar with the idea of the domain and the range of a function. So let's go to another function and look at the domain and the range of that function. We will consider the next example or the next function as example 2. And for example 2, what we are given is f of x equals 1 over x. And what we want to get to is to be able to determine the domain and the range. So the easiest way to go and determine the range and the domain here is to quickly maybe attempt to sketch even the function. So if you look at our function, you should be able to spot it, that what it is a hyperbola. I think you must have done this when you were doing grade 11 and sometime when you were doing grade 12. So this is a hyperbola. Okay. And if you look carefully for our hyperbola, we quickly need to determine our vertical and horizontal asymptote. And if you remember, the general form of a hyperbola is usually a divided by x minus p and then plus q. And what is going on there is that our q here is usually y is equal to q, which is our vertical asymptote. And we also have our horizontal asymptote. So what usually happens is you look at the equation which is here, and we usually take x minus p equated to 0, then solve for x. Then we'll always have x is p, and this one here becomes our horizontal. This here, sorry, it becomes our vertical asymptote. So the other one is our horizontal asymptote. So this is our vertical asymptote. And the y is equal to equation should be our horizontal. Silly mistake there. My apologies. So that is our horizontal asymptote. Okay. So if you look at our problem, we quickly need to establish our horizontal and vertical asymptote. And just one more thing. If you remember from back in the days, if the a is greater than 0, meaning positive, your graph for your hyperbola would usually be on the first quadrant and also the third quadrant. But if the a is less than 0, meaning a negative, the graph is usually, when you look at the quadrants as far as the asymptotes are concerned, it's usually on the second and the fourth quadrant. So let's go and look at our f of x and try and establish a plot. So if you look at our f of x, you will see that what we have is 1 over. At the bottom, since we can't see anything, we can put x minus 0 plus 0 even there. So what this means is that we will have our horizontal asymptote y is equal to 0 as that. And also we will have our vertical asymptote as x is equal to 0. So this will be our vertical asymptote, while the other one becomes our horizontal one. So let's go ahead and plot our graph and see what we obtain. Because essentially what is going on here with this horizontal asymptote, it means we are not supposed to touch the x is 0 line, because remember, in asymptote it is a line which you are supposed to get close to, but the graph is never supposed to touch that line. So let's go ahead and quickly put in our Cartesian plane, and I'll quickly highlight my asymptotes. So we have a blue for the horizontal asymptote. So remember, we have x, we have y. So our horizontal asymptote is at y is 0, and we know that y is 0 on the x-axis. So on the x-axis, I'm going to go and dash it like that, so that I remember not to touch that line, because in asymptote, we are not supposed to touch. Then now we deal with the vertical axis, which is x is 0. So we know that x is 0 on the vertical axis or on the y-axis. So that's why I'm going to do that. So it means my graphs, when I draw them, they are not supposed to touch any of these. And as you can see, our a is equal to 1. So which means it's positive. So our graph will simply be on the first quadrant and on the third quadrant like this. So now we need to go and worry about finding the range and also finding the domain. Y is 0. So let's start by looking at the range. So if we look at the range, remember the range is the set of y values for which the graph is defined. If you look carefully, the graph has increasing and positive y values, but it cannot touch the y0 line on that portion. But on the other portion, if you look carefully, it has y values that are going down in the negative. So the y values, we have positive ones going up and up, we have negative ones going down and down in the blue arrow, but we are just not supposed to touch y is 0. So we can write this in two ways. So someone can say y is an element of real numbers like this, because y can be negative and positive, but also make sure that they make it a point that y does not include 0. So we're excluding y is 0, because the y is 0 is our asymptote, and remember, the asymptote is a line which you are not supposed to touch. So this is one way of writing the range. Someone else would prefer to say, I will just look at the portion from y is 0 going up. So I will just say I have y greater than 0, and when they look at the other portion of the graph, which will be that portion going down, this one, they will say, oh, there we have negative y values, so I'll just say y less than 0. So as you can see, this exclude the y is equal to 0, and both answers would be correct. So let's have a look at our domain. And remember, for domain, we said it is the set of x values for which the graph is defined. So when we look at our domain, you will come to an appreciation that our graph is in existence on the left, on the right of x is 0. So remember, the red line is x is 0. So we have x values after 0. So we have an x is 1, x is 2, and so on. But we are not supposed to touch x is 0. And also on the left of the x is 0 line, we also have our graph. And our graph, the x values can go as far as they want to the left, meaning to negative infinity. So our domain can also be written as x is an element of the reals, but what we are going to do is we are going to make it a point that they know that x cannot be 0, because x is 0 is our asymptote. So this is one way you could write that. Another way is you could say, I have x values that are greater than 0, and I have x values that are less than 0. My graph doesn't exist at x is equal to 0. This would be the range and the domain for your example 2. I hope this makes a lot of sense. Let's go to example 3 and see if we are able to determine the range and the domain. Our example 3 is up on our screen. So let's go ahead and determine the range and the domain of this function. And this one is going to be a bit interesting because of how it looks. So let's go to step number 1. And what we need to do is to quickly find the x-intercepts, because it becomes easier once we have plotted the graph to be able to figure out what is going on. And on the x-intercept, what we know is that our y is always equal to 0. So our y is equal to the square root of 1 minus x squared. So when I set y to be equal to 0, what we have is 1 or square root of 1 minus x squared. Then what we can do is we can just square both sides to remove the square root. And when you square both sides, what you will come to in appreciation is that you will have 0 equals 1 minus x squared. And you can transpose this such that you have x squared minus 1 equals 0. And this, when you factorize, you get x plus 1, x minus 1 equals 0. So which means you get x is 1 or x is minus 1 as our intercept. So if you write this as a coordinate, in coordinate form, you will see that what we will have is 1 and 0 and minus 1 and 0. So let's go to step number 2 and quickly find the y-intercept. So what we know about the y-intercept is that it is at an x value of 0. So we can just go ahead and put in the square root of 1 minus 0 squared, which is going to end up giving us a 1. In fact, because you are taking a square root, someone would argue that you are actually going to get a plus or minus 1. But let me leave it as plus or minus 1. You will see why. So what I need you to actually remember is that you need to remember how to plot your parabola. What you need to remember is that this actually is an inverse of a parabolic function, what we have here. So f of x is actually an inverse of a function which you know how to plot easily. It is an inverse of g of x. So if I quickly find the inverse of f of x, which will give us g of x, you will see how the graph is supposed to look. So for example, let me quickly find the inverse, which will be just x equals 1 minus squared. Then we square both sides. When we square both sides, we get x squared equals 1 minus y, it becomes y minus like that, and then I transpose this. Then what you will see is that what we have is x squared plus y squared equals 1. So if you think carefully, this is more like a circle. This is what we have. It is more like a circle. So if you go ahead and plot this here, what you will see, because now you have an idea that what we have is actually a circle. But since we are making y the subject, it means the circle will be above the x-axis. So let's go ahead and quickly plot that. So you'll have your Cartesian plane like that. And what you will come to a realization is that you will have your x and then your y. So the graph which we are looking at will be something which is like this here. It will be, where's the x-intercept? So if you look at the x-intercept, we found one at negative 1 and 0, and the other one we found at 1 and 0. But here, the plus or minus, when we take the square root of 1, that's where, when you work in reverse, it's easy for you to see these things. So the y-intercept, if you think carefully, it means it will just be at positive 1. So it will be at 0 and 1, which you had found. So when you quickly draw this, you will see that your function looks something like this. That is how your graph looks. And that is our f of x. So now with our f of x up and running, let's go ahead and quickly find our range and domain. So let's quickly have a look at our range first. So remember, our range is the set of y values for which the function is defined. So if you look carefully, we have y values starting from 0 going up, and we have y values there, we have y values there. But if you look at the biggest y value which we will ever have, it will be that 1 which is sitting at that point there. So essentially we can just say our y is an element. If you look carefully, we have y values which are 0. It is an element from 0 up to a maximum y value of 1. That is what we have as our range. So the minimum y value will be 0, but when we go up at the top here, what you have is a y value of 1. So that is why our range will be from 0 to 1, and these are included. Okay. Alternatively, someone else would write this as y is between 1 and 0, like this. And the answer would still be the same. You would still get all your marks. Now let's have a look at the range. Well, the range we are done. Let's have a look at the domain. So remember the definition of the domain. It is the set of x values for which the function is defined. So I need to look at the x's and say, where is this function defined? Do I have limits on the x values? And when I look carefully, you will come to a realization that the only x values which we have is just from -1 up to +1. We don't have an x value of 5 for this curve of ours. So we'll say x is an element from -1 up to +1. This answer would be correct. Someone else would choose the notation to say this graph has x values which are between 1 and -1. Both notations are correct. So I hope now you understand the idea of range and domain. So let's go to example number 4, where we are looking at a question which is phrased slightly different, but we'll just do it. Okay, let's have a look at example 4. So for example 4, we are given a function f of x, which is x plus 1 over x. And we are asked two questions. We are required to find f of 2 and f of a. So essentially what f of 2 is, the simplest of terms, it is simply the y value when x equals 2. That is what we are looking for. So what is the y value of the function when the x is equal to 2? That is what we are looking for. So which means our f of 2, wherever we see 2, we'll just go and wherever we see x, we'll replace it with 2. So we'll have 2 plus 1 over 2 there, which will end up giving us 2 plus that will be 2.5, which is 5 over 2. So there's their answer. Whoever is asking us this question would be very happy. It's an easy question. Then if we look at f of a, so essentially what the question is, what is the y value of the function when x is equal to a, whatever a is? So that means we'll just go to our equation, and wherever we see a, we put in, wherever we see x, we put in a. So this will just end up being a squared plus 1 all divided by a. And with this, we are done. So we'll now look at example number 5 and see how do we tackle that question. Our example number 5 is up on our screen. So we are given g of x is equal to 2x plus 1 divided by x minus 2. And the first question is that we should find the domain of g of x. So I'll quickly separate the two questions. So if we think carefully about g of x, what you should realize is that once we make x to be equal to 0, or not to be equal to 0, but once x is equal to 2, what we will have is we'll have a division by 0. So it means that x is 2 is one of those values which we never want to have on our function. So if you think carefully, x is equal to 2 will be our asymptote actually. It will be your asymptote. So it will be the line which we are putting there saying you should never touch it, because x, when we make x to be 2, the denominator will be 0 and the division by 0 is undefined. So it means that there's no other x value, if you think carefully, which we can put in there and we get anything which we don't want. We can put in 1, we can put in 0, we can put in 5. All of them will give us a corresponding y value. So our domain here will be easy. It is all x values excluding x is 2. So our x will be an element of real numbers excluding 2. Okay, this will be our domain. And someone else would choose to write it slightly different. I'll show you now. So someone else would choose to say, I will say my x must be less than 2 and my x must be also greater than 2. And this would still be a valid answer, because all what you are saying is on the right of 2, my function is defined. On the left of 2, our function is also defined. Now let's go to the second question where we need to do g of minus 1. All what that means is wherever we see x, let's go and put minus 1. So we'll have 2 minus 1 plus 1 divided by minus 1 minus 2. This will end up being negative 1 divided by negative 3, which will just be 1 over 3. That is how we find g of minus 1. Now let's jump to the next part of our session where we will be looking at the vertical line test. So the vertical line test is going to help us to be able to determine which function or which given expression is a function and which one is not. So let's have a look at the vertical line test. So while at the vertical line test, we need to ask ourselves exactly what is the vertical line test telling us. And what it's telling us is simple. As long as we draw a vertical line and it touches the graph at one point, whatever function you are looking at or whatever graph you are looking at is a function. So the vertical line test, by definition, will state that f is a function. Let me just say f of x is a function. So our f of x will be considered as a function if the vertical line, so we'll draw a vertical line on the graph. If the vertical line touches the graph at one point. And the one point is very important that we make sure that we meet it. If it touches the graph at one point, then it is a function. However, equally so, f of x is not a function if the vertical line crosses the graph at more than one point. So please make sure that you know this definition. So let's quickly jump into examples and quickly establish what is a function and what is not a function. So let's quickly have a look at a couple of graphs. So we'll quickly determine if these are a function or not. So if I have my Cartesian plane here and I have a graph that looks this way, The graph is going like that. So what I'm going to do is I'm going to quickly use the vertical line test to determine if this is a graph or not. So I'm just going to quickly draw a vertical line, and if you look carefully, it only touches the graph at one point, and our graph here is given by the equation y is x cubed. So y is x cubed. So if you look carefully, we are touching the graph at one point. So our y here will be considered as a function. So our y is a function for the graph which is above here. Okay, I hope that makes sense because we passed the vertical line test. Remember, for a function, we said we must just cross at one point. But let's have a look at another one just next to it. Let's have a look at a circle. See if I can quickly draw one. Let's have a look at a circle as an example. If you look carefully, for our circle, when we draw the vertical line test, it is not going to pass. So if I draw the vertical line test, remember I said f of x is not a function if the vertical line crosses the graph at more than one point. So it crosses the graph there, but it also crosses the graph there. So that's the first point. And here, that's the second point. So as you can see, our f of x here, which is a circle, will definitely not be a graph. So this is described by the equation x squared plus y squared equals 1. So I will say here, this is not a function. Because it fails the vertical line test. So let's have a look at another function and test it if it is a function or not. So let's have a look at this one. And I think this one you've done it a couple of times from high school. It is just the inverse of a parabola. So the graph which we have looks this way, like that. So it's the inverse of a parabola. So you'll have your x, you'll have your y. So we just take our vertical line and we start our test. So I draw my vertical line and I see that there's a problem. I'm crossing there and I'm crossing there. So I'm crossing at 2 points. So that is my first point. And down here we have our second point. And this does not look good because we said that a function should pass the vertical line test, which means it should only be crossed at 1 point. So the equation for this graph is that. So as you can see, we will say that our y is not a function. And because it fails the vertical test, the vertical line test. And this goes back to what I said earlier, where I said different x values can give you the same y value. But once different y values are mapping to the same x value, that is a problem. So if you think carefully, we have a situation where you have different x values giving you the same y value, and that will usually be called many to one. So let's quickly make a note. So if you have different x values giving you the same y value, that is called many to one, meaning many x values to one y value. And what you need to come to an appreciation is that when you have many to one, that is a function. A good example of this is our parabola. And when you now have a 1 is to many, that is when you have different y values, but they are mapping to the same x value. That is not a function because it will fail. For example, if you think carefully, here, if we use this as an example, if we use a 2 as an example, the y value which will be sitting there will be at a square root of 2, and the y value which will be sitting here will be at negative square root of 2. So do you see that you have two different y values for the same x value? That one is called 1 is to many, meaning one x value to many y values, and that is not a function. So make sure that you do understand the idea of 1 is to many and many is to 1. This brings us to the end of the first part, which is just an introduction to functions. Now what we are going to be looking at is piecewise defined functions. Let's start off by defining what is a piecewise function. So let's quickly have a look at a definition. So by definition, a piecewise function is a function where the formula changes on different parts or on different parts of the domain. So it is a function where the formula, you will see when we sketch this, changes on different parts of the domain. So that is how we define a piecewise function. It is a function where the formula changes on different parts of the domain. So let's go ahead and start off with an example so that you come to an appreciation of what we mean. So let's consider a function which is given by f of x. So this will make it to be example number 6, if I'm not mistaken. Yes. So this will be example 6. So if you look at example 6, what we are given is f of x is going to be equal to x, and then we are going to have x squared, and then we are going to have 1. Very easy functions, 1. So the x is going to be defined for x values which are less than 0, and the x squared 1 is going to be defined for x values which are between 3 and 0, and then the y1, or the 1 which is 1, will be defined for x values which are greater than 3. Okay, so let's have a look at what this means. So if we look at this graph here, what this means is that we have a couple of functions here. So we have a graph, which I'm going to highlight in blue. So that graph is equal to, so we have a graph which is going to be y equals x, but that is only for x is less than 0. That graph is for x is less than 0. So meaning we'll only plot that graph for x values which are less than 0. But then we have a second portion of the graph, which is this one here, x squared. So if you look at our x squared, that means we have a graph which is x squared, and that graph is valid between x is 3 and x is 0. So meaning I'm only going to graph it or plot that graph between x is 0 and 3. And then we have the last one, which is at 1. So which is that last portion of the graph. That last portion means that our y will be 1, and that will be 4. This is supposed to be greater than 3. Let's quickly fix that. So this is supposed to be greater than 3. So that there will be x is greater than 3. So I need to plot these three graphs on the same graph and see what we obtain. So let's quickly push these to the next page for more space. Okay, so let's zoom in. So let's quickly put in our Cartesian plane and see how best we can plot all of these. We have our x and we have our y. So what I'm going to do is I'm going to start off with the blue one, the blue graph. So what you should know by now is that the blue graph y is equal to x. Y is equal to x is usually a function that moves like that. That is usually the y is equal to x function. It moves like that. But if you look at the x value, we are saying this graph should only be valid for x values which are less than 0. So that means for x values which are positive, I actually need to go and erase it. So I'm going to erase it this side because all those values there are positive. So I need to erase it. But also, if you look carefully, 0 is not included. So it is not included. So which means there at 0, I need to make a circle like that, which is not shaded. So essentially, I'm done plotting my green graph because it is now existing to the left of 0. So for x values which are less than 0. Now let's go for the gold one. So for the gold graph, what you know is that x squared usually looks something like this in totality. It usually looks something like that. It usually looks like this, and it goes on and on. That is how x squared looks. But when I look at the x values, they are saying this graph is valid from 0 to 3. So it means the x's before 0, I need to now erase that part because in the negative side, this graph is not there. But on 0, if you look carefully, it starts there and it's included. So which means I need to shade and have a blue and a gold shade there. But then it ends at 3. So which means if I have an x value of 3, somewhere here, let's make it to be black. If I have my 3 somewhere here, this is where the graph ends. But that is included also. So it means I need to have a circle here. And the corresponding y value, when you put in x is 3, you get in a 9. So I need to erase everything after x is 3 because that gold graph is not defined there. That is how we plot it. Now we need to go to the last part, which is y is equal to 1. So if our 1 is somewhere here, you should now know that y is equal to 1 would simply be a straight line like that. But I now need to look at what are they saying. They are saying that y is equal to 1 is valid for x values that are greater than 3. So it means I need to erase it for these x values which are before 3. So I need to erase it there, erase it even there, erase it even that side. Then when I get to 3, it can go to the right because x is greater than 3. But if you look carefully, here we didn't include the 3. So it means I should just go and write or make a circle there. And this would be my piecewise function for the graph that is above. So make sure that you are comfortable with doing these calculations and you understand how to plot the graph separately. Okay, so let me give you another example just to get a feel of what is going on. Let's call it example 7. So there is our example 7. We are given that f of x is the absolute value of x. And what we are required to do is to plot f of x. And by now you should just remember that those two straight lines, all what they mean is that they mean absolute value. And with absolute value, all what it means is that the function, whatever which is inside, can be negative and it can be positive. That is what this means. It means that whatever which is inside it can be negative and positive, but those signs will make it to be the same at the end. So this means that when we break up our function, actually our f of x, you will see that this function can be negative x and it can be positive x. But because we always want it to be positive, I just need you to give it some careful thought. Because we always want to be positive, we want the function to end up giving us positive values. The negative part of the function, negative x, will need to have x values that are negative. So less than or equal to 0, so that we can get negative or positive values at the end. And the positive one must have x values which are greater or equal to 0, so that we end up getting the positive part. So we can choose one of them. We shouldn't include, so we can choose either one. So let's exclude the negative one. So let's go ahead and plot this. So this graph should be extremely easy because you know how to plot that graph separately. So the blue graph, clear highlighted, is easy to plot. You've probably dealt with this many times back in high school, because the blue graph, all what it is y is negative x for x values that are less than 0. So meaning the negative side of things. Then the other one, which is gold, all what we have is simply y equals x, and this will be for x values which are greater or equal to 0. So let's go to our Cartesian plane and quickly plot this piecewise function. So I'll start with the gold one. So the gold function y is equal to x. Typically how you would draw it, you would know that you just go like that, and that's your function. But when you look carefully, we are saying here only for x is greater or equal to 0. So meaning where x is negative, we need to go and erase all that part. So this part needs to be out. That's why I'm going to take it out. And if you look carefully, we are including the origin. So I'm just going to make a solid dot there. Now let's go for the blue one. So y is negative x. You would typically draw like that. That would be your y is negative x. But then when you look carefully, you see that they say, aha, for x values which are less than 0. And remember that x is less than 0 in that direction, and x is positive or greater than 0 in the other direction. So x is greater than 0 in that direction. So that means I just need to erase that bottom portion there. And then because the blue function is excluded, I'm just going to draw a circle there. And this would be what constitutes our piecewise function. Let me just make the length to be much more the same. So this is what your function would look like. F of x equals the absolute value of x. And from here, there's many other functions which you can plot, which I'm going to leave up for you to go and find. We'll jump to the next section, which will be looking at composite functions. So let's start off by quickly defining what are composite functions and how do we make them up. So let's have a look at a definition. So the definition is as follows. Let f and g be functions. The composite function, which is indicated by this, is defined by, so if we say f composed with our g, the answer is simply f of g of x. So how you would usually pronounce this is you would say that f is composed with g. So f is composed with g. So essentially we are making f to be a function of g, of which g is a function of x. So let's look at an example to quickly understand what is going on. Our example will be example number 8. So for our example 8, the first question requires us to find f of g of 1. So essentially how this works is, think of it as when you are looking at f, wherever you see x, you are going to replace it with g of x. But in this case now, for our g of x, they want us to find g of 1. So which means for our f, wherever we see x, we are going to replace it with g of 1. And how do we find g of 1? We'll take g of x. Wherever we see x, we put in 1. So let's take a two-stage approach. So let's go and find g of 1 first, which if you look carefully, I have the function, it will be 1 over 1 minus 3, which will give us a negative half. So now that I have g of 1, it means it's easy now for me to find f of g of 1, because all what I need to do, wherever there's g of 1, I replace what I found it to be. So it means I'm looking for f of minus 2. And once you have f of minus 2, it means I need to go to f. Wherever I see x, I put in negative half. So this is easy. So let's go to f of minus a half. So I go to my equation. For my f, I have 2 times wherever I see x, I put in a half, and then plus 1. If you look carefully, this will be negative 1 plus 1, which will give us 0. That is how we find the answer to that question, f of g of 1. So let's now have a look at b, where we are required to find g of f of 2. So it means what I need to do is to quickly start by working off what is inside here. What is f of 2? So if you look carefully, my f of 2 will be, wherever I see x, I'm going to replace it with 2. So I'll have 2 plus 1, and if you look carefully, this will be 5. So this means that if I'm looking at g of f of 2, this is the same as doing g of 5. And now I just need to go and apply my g formula, because I'll say just my x is 5 when I'm looking at our g. So when we go to our g of 5, wherever I see x for our g, from our g formula, I'm going to put 5. So I'll have 5 minus 3, which is going to give us 1 over 2. I hope this does make sense. Let's go and have a look at question C. So for question C, we are required to find f of g of x. So essentially, we are required to find f g like that. What this means, if you remember, it is f composed with g. Okay, so if it was g of f of x like this, this would simply be g composed with f, and this what would mean is that we have g composed with f. Okay, so this is what the second part would mean. So let's go ahead and deal with the first part, where we have f composed with g. So if you remember, our f of x is 2x plus 1, and our g of x is 1 over x minus 3. So what this means, when we have f of g of x, it means that we will go to our equation f. Wherever we see x, we put in g of x. So meaning I have 2 times g of x plus 1. And if you think carefully, this will be 2 into our g of x is just 1 over x minus 3, and then plus 1 like that. So essentially, our f composed with g will end up giving us a hyperbola. So our f composed with g will give us 2 divided by x minus 3 plus 1. That we have found there. We needed to find f composed with g. And for our D, question D, we are actually required to find g composed with f. which is what we had written already. So we are required to find g of f of x. That is what we need to find, and I've explained what it is. So let's go ahead and sub these. So we already know the formula for f and g. Our f of x is 2x plus 1. Our g of x is equal to 1 over x minus 3. So if now they are looking for g of f of x, this means wherever I see x, I need to go and put in g f of x. So it means I have 1 over f of x minus 3, like that. That is what I have. So, and this will be equal to 1 divided by my f of x is 2x plus 1 minus 3. So our final answer, g of f of x, will simply be equal to 1 over 2x minus 2. And whoever is marking will be very happy with you. So I hope this idea of composites makes a lot of sense. Whenever you are asked to find the composite of one function with another, or one function is composed with the other one, you should be comfortable to do that. The next part of the session is on even and odd functions. Okay, so let's have a look at even and odd functions. And I'm going to give you a mathematical definition of what is an even and an odd function. So how are we going to determine if a function is even and odd? So for even functions, we have a property which we are supposed to test, and if it passes, the function will be an even function. What we need to test is that is f of x equal to f of negative x? Meaning if you put a positive x in the function and a negative x of the same value, do you get the same y values? If that is the case, then that function will be called an even function. Then for odd functions, but this, let me just write them and say they are important properties. And then let's quickly have a look at how do you classify or determine if a function is odd. So odd functions must make sure that they meet this important property here. When you find f of negative x, it should be the same as negative f of x for an odd function. This should always be true. But also what you need to remember is that there are functions which are not odd and not even. So functions that do not meet the two properties here will be functions which are not odd and they are also not even. So to get an understanding of it and of an odd and even functions, let's go straight to examples. And the example which we'll be looking at will be example number 9. For example number 9, we have our question on our screen. Is f of x equals x squared odd or even? Well, I know that I need to do two tests. So I need to try maybe test 1. So test 1, remember, if I'm testing if it's even, I should see if f of x will be equal to f of negative x. If this is the case, then the function will be even. So which means, as you can see, my f of x is x squared. So I need to do my f of negative x, which means wherever I see x, I put negative x, I square. But negative x squared, we all know that it will end up being a positive x squared. So as you can see, our f of minus x is x squared, which is the same as our f of x. So if you think carefully with this, you should be able to see that, this is actually an even function. Why is it an even function? It is an even function because we found out that our f of x is the same as f of negative x. That is what we found out. So let's quickly take example 10. So let's have a look at example 10, which is f of x equal to x cubed, even or odd? So what I know is that I need to somehow, or I'm given f of x is x cubed. So I know that as part of my check, on both of them, I need to always have f of negative x. Then I can compare with the answer which I get. So let's go and find f of negative x here. So we have f of negative x, meaning wherever we see x, we put negative x. And when you have negative x cubed, the answer will simply be negative x cubed, like that. And when you look carefully, you will see that what we have here is simply our f of x. So if you look carefully, you'll see that our f of x is equal to, we have the negative of f of x, because that x cubed there is just our f of x. So as you can see, what we have is that our f of negative x will be equal to negative f of x, and that is a necessary property for odd functions. So this means that f of x is x cubed is an odd function. Okay, it is an odd function. Let's have a look at the last example before we end the session, and you can do a lot of practice by yourself. Let's have a look at example 11. So for example 11, we are required to determine if f of x equals x minus x squared, if this is odd or even. So I'll quickly note down my f of x, which is x minus x squared. So I'm going to find my f of minus x. So meaning wherever I see x, we put in negative x. So if I look carefully, I will end up having negative x squared. So when I look carefully, if I pull out the negative, what I have is I have x plus x squared. And when I look carefully at this function, it is definitely not going to be equal to f of x, but also at the same time, as you can see, it is not going to be equal to negative f of x. So this means that this is not even, and it is also not odd, because if you think carefully, f of x, as you can see, it is x minus x squared, which means negative of f of x would be x, or would be negative x plus x squared. So as you can see, what we got here didn't amount to any of that. So that is why we can safely say that our f of x equals x minus x squared is not even and not odd. So there are functions which are not even, and they are also not odd. So make sure that you do more practice questions in order for you to understand the concepts. I hope this was helpful and good for you to get up to speed. So do more practice questions. I wish you the best. Bye-bye. Please don't forget to like, share, and subscribe. Take care.